The Pythagorean theorem can be used to also determine if triangles are right triangles or not. Basically, if the Pythagorean theorem is true, it is a right triangle. If it's not true, then it's not a right triangle. Now, if you're looking at these three examples, you'll notice immediately there are no right angles marked. But if you remember, I told you the hypotenuse is always the longest side. If it's going to work, it's going to have to be the longest side. So what I set up is that 5 squared, is that equal to 4 squared plus 3 squared? If it comes out true, it is a right triangle. If it comes out false, it's not. And so I have 25, is that equal to 16 plus 9? 25 is equal to 25, therefore it's a right triangle. And it's as simple as that. Now this one initially seems complicated or scary. Using my common sense, I'm pretty sure that the square root of 8 is the biggest number. If you're not sure, use your calculator quick to get an estimate, but then always go back to the exact. So I have the square root of 8 squared. Is that the same as the square root of 5 squared plus the square root of 3 squared? When I check that out, I end up with 8. Is that the same as 5 plus 3? Because the square root of something squared cancels. 8 is equal to 8. Therefore, this is a right triangle also. And in checking our last example, here's my biggest side. So 13 squared, is that equal to 11 squared plus 5 squared? Is 169 the same as 121 plus 25? Is 169 the same as 146? Well, that's not true, so therefore this is not a right triangle. Now this leads to the question, well, what kind of a triangle is it? And if we go back, first we have to talk about Pythagorean triples. You may have noticed a pattern with some of the numbers. And Pythagorean triples are sets of numbers which make the Pythagorean theorem true. So for example, some common ones are 3, 4, 5, and 5, 12, 13. Now the cool thing is, not only is it those numbers, but it's also multiples. Work also. And so for example, if I multiplied everything by 2, that would give me 6, 8, 10 as a triple, or 10, 24, 26 as a triple. And it's just a way to kind of have a shortcut. If you see 3 and 4 as the legs of a right triangle, you know the hypotenuse is 5 without doing the Pythagorean theorem because it's one of the triples. Just a little shortcut. But back to our review. Way back, we learned that the triangle inequality theorem helped us figure out that the length of any two sides of a triangle has to be greater than the third side, otherwise the triangle can't be formed. And so that gave us this cool set of inequalities. If we go through and solve these inequalities, then we can get a range of values for a particular triangle. So in this case, we are going to say 4 plus s has to be greater than 7. 7 plus s has to be greater than 4, and 7 plus 4 has to be greater than s. Those are my three combinations. If I solve each one of these, s has to be greater than 3, s has to be greater than negative 3, and 11 has to be greater than s. Well, we can't have a negative, because that just doesn't make sense. And this one give me my lower and upper bounds. And if you flipped your inequalities around, what you'd find is that s has to be between 3 and 11. Now this is review. This one, still hinging on the review, we're dealing with an isosceles triangle. Oops, I don't need the line down the center. Dealing with an isosceles triangle. If it's isosceles, these two sides are equal. The base is 13. So what has to happen is that a plus a has to be greater than 13. A plus 13 has to be greater than a. And 13 plus a has to be greater than a. Now if I work this top one out, I end up with 2a greater than 13. A has to be greater than 6.5. These two work out the same, and they work out kind of strangely. If I subtract a from both sides, I end up with 13 must be greater than 0. That doesn't make sense. It's a true statement, but it doesn't seem to help me solve my problem. This is my bounds. And if you think, well, maybe this means that a could be just anything greater than 0, try 1. If we let a be 1, this one right here will be false. So my answer is that a has to be greater than 6.5. Now this leads us to right triangle relationships. And there's a couple of key factors. If the Pythagorean theorem is true, the measure of c is 90, therefore it's a right triangle. If that c squared is greater than the sum of the squares of the other sides, then your angle C is greater than 90, which means you have an obtuse triangle. And if your C squared is less than the sum, then your angle C is less than 90, and therefore you have an acute triangle. Now, very important, notice the order. We always want C squared first when we look at our comparative values. So if we look at a couple of examples here, my biggest side is my hypotenuse, 10 squared, and we're going to use our elementary model of fill in the blank. How is 10 squared related to 5 squared plus 7 squared? Well, 100. How does that relate to 25 plus 49? Well, 100 in relation to 74. Well, of course, that means 100 is greater. Therefore, this is an obtuse triangle. B is a mistake, because if you check the inequality theorem, that can't even be a triangle, so we're going to skip that one for now. And if we look at C, how does 5.2 squared compared to 3.8 squared plus 4.1 squared? With a little bit of calculator work, we end up with 27.04. How does that compare to 14.44 plus 16.81? How does 27.04 compare to 31.25? Well, obviously it's less. Therefore, this is